Well, good afternoon, everyone. Welcome to our Thursday afternoon energy symposium. A little bit of admin for next week. We're going to have Dr. Barbara Berger from Chevron Technology Ventures. She's the Senior Vice President of Chevron Technology Ventures. She'll be here to tell us to talk about what Chevron is doing in technology and advancements. And it should be interesting because she made a request. She goes, Fred, if you don't tape it, I can be open and frank. So for the students, we are not taping next week because she promised to be open and frank and not go to by a party line if we turn off the video. So maybe entice you a little bit to come next week. Maybe you hear something more interesting from Barbara than she would normally be able to say. Today we have Juan Torres from the National Renewable Energy Lab. He's been down here, I guess, a little bit visiting before, but this is the first time we've had an opportunity to have him come speak to us. He spent 27 years at Sandia National Labs, so he's got quite a bit of background in the energy and technology area and working in cybersecurity as well. He came in town. He attended the Grid Next conference up in Georgetown on Monday and Tuesday. Been doing some tours around campus, and we've got him this evening. So without further ado, Juan, it's all yours.
All right. Thank you. Thank you. Thanks. So let's see. Maybe start out with how many of you know anything about NREL? A few? Yeah, that's actually pretty good. Usually it's very few people, especially this part of the country, right? In Texas, a little bit further away from. You don't have a national lab, so I'm always surprised by the size of the state that we don't have a national lab there. So we'd be more than happy to be a surrogate. Yeah. Is that right? Okay. All right. So maybe ask the other questions. And I know I had lunch with some of you folks here. If you remember, how many national labs are there? 17. All right. Okay. You guys were listening. So I don't know if any of you have really considered what is a national lab, why do we have these, and so on. NREL is just one of the 17 labs working in the energy space. The national labs kind of go back to the nation's history tied to the Manhattan Project. The majority of the labs, actually, not NREL specifically. History at NREL is focused around the energy crunch in the 70s, which is way, way before all of you were born. But we were dealing with the major energy crunch back in the 70s, trying to find different alternatives, and solar being one of them, as well as wind. A couple of options. And I think back then we had no idea where we'd be. We were always hoping as a nation we would find other options. So, but I think the big point is that NREL is not just about renewables, and that's one of the things I want to point out. I came to NREL after 27 years at a nuclear weapons lab at Sandia Labs. They were a core part of the Manhattan Project, and they it's kind of the engineering arm. So people always ask me, given I've only been at NREL for 4 months, how is it different? How is NREL different than Sandia and, say, Los Alamos? And the way I describe it is I feel like I got my ankle bracelet removed. And the reason is, so Sandia is actually a very special lab. It's the largest lab at 11,000 people. About half of those are technical, so then you're talking about 5 to 6,000 technical staff, and about half of those PhDs. So that's a lot of engineers, a lot of high caliber folks, and so the real big difference there is the fact that they do primarily a security kind of work, national security work, but I did manage their renewables program as well. And I think there are a couple other differences. They're the only lab on a military installation. So now I work at a lab that's much more open. We do a lot more work with the private sector. We have more partnerships with external entities than any other national lab. So 2,000 people there, and we do that much work with not just the private sector, with academia, but also with some of the foreign entities, foreign governments, and so on. So it's a great place to work. If you have more questions, catch me after. More than happy. But you can go to nrel.gov and find out more about what's going on at NREL. And it is much more than renewables. So the talk I've got today is around this area about grid technology, and specifically around where renewables fit, but I'll broaden it as well, because there are a lot of opportunities with what's going on in the grid and grid modernization. I'll touch base on some of those. Renewables being one big aspect of it. We're in a whole different place than we thought we'd be a few years ago, and depending on where you are in the country, like Texas, that penetration of renewables is significantly higher here than in some other areas. I think a lot of it is set in motion, not just through technology, but of course all the policy that incentivizes people to use this. So that's something I usually tell folks, especially coming from a technical perspective, is that technology is only one part of the solution here. We really have to look at the business models. How does using these technologies, how does this actually get supported, financed, as well as regulatory aspects, as well as standards and codes and all those things. So they all have to come together and align to work well. So the focus at NREL really is around science and engineering of these different technologies that are now part of our energy infrastructure. So when we're talking about what those things are, it includes the generation sources, but it also includes how we move the energy. It includes the grid. It includes how we use energy. So it includes the end use, the things like how we're managing energy within our home energy management systems, building energy management systems, and how that can also be an active part of how we use energy as a whole. In the past, that really wasn't how things were used before. We pretty much just kind of sat there and we flipped the switch and expect electrons to flow our way, and that was about it. So now we have a very, very, very different model. Just a little more background about NREL itself. There are essentially three major core capabilities. One around analysis system integration, so taking a look at the big picture. Around innovation, which is primarily our innovation, our engineering kind of capability. And then some of the fundamental science that supports these around materials, biological systems, and so on. So we do quite a bit also in biofuels outside of my area, but that's a big area. And then at the bottom here is this what we call kind of cross-cutting elements. So we have quite a bit of work going in computation, in visualization, high-performance computing. So the computer area is very important. So this is a vision that we have for what we call energy systems integration at NREL. So adoption of reliable, affordable, secure, resilient, clean energy systems, and at a pace and scale that matters. And we say that now because what we thought was high penetration of renewables a few years ago is very different than what it is today. At some point, we were thinking, if we can get 10-15%, then we're pushing the envelope. That's kind of where we are with renewables, but there are some states that have set much higher goals. Texas being one, I think California. Hawaii is trying to get to 100%. Essentially, they're weaning themselves off of fossil fuel. They use primarily diesel generators for their electricity. They have a coal plant as well, which is very surprising to most people. That a state like Hawaii is so reliant on fossil energy. And imagine what the cost is to get fuel out there. What do you pay for electricity here? 10 cents. Okay, so Hawaii, depending on which island, it can go anywhere from 30 to 45 cents, even more, per kilowatt hour. Imagine paying for a studio apartment $400 a month for electricity. That's kind of where they're at. So they want to do what they can to reduce their dependency on fossil-based energy and use some more renewable energy. So this, one of the things that we're seeing is that there's a big increase in the penetration of different types of resources. Wind, the cost has gone down significantly. And I'll give you my opinion of how we've kind of essentially cheated by to get there. Same thing with solar. Not quite at the same price, but we're getting there. And the big focus has been on efficiency around solar cells. On the topic of wind, so where's the big challenges now? Big challenges on wind integration. Well, the focus in the past has been more efficient turbines, lower cost turbines. Where we're going now is more efficient and more productive power plants, so operation of an entire wind farm as a system. So what we're finding is that through doing a lot of analysis of wake turbine-to-turbine interaction kind of analysis is that it doesn't make sense necessarily when you have rows of turbines for your first row of turbines to maximize its energy capture. It actually might make sense to let some of that wind energy pass through. So you can actually turn your blades and feather them a little bit so that they let more of that wind energy through to the subsequent rows. So as a system now, we're increasing the overall output of a generation system. So that starts leading to how do you operate and control these as a system of a whole bunch of turbines. Okay, so now you're thinking about advanced controls, complex systems and complex interactions. Requires sensing and so on. The other thing in the wind space is that the turbines are getting bigger and bigger. So you look at offshore, terrestrial land-based wind turbines. The most popular turbines tend to be in the 2.5 to 3 megawatt size. And you can see much, much bigger ones over if you look at offshore turbines, and those can go 7, 10 megawatt scale. We were doing some work in the national labs to look at 50 megawatt wind turbine. Imagine the size of such a turbine, right? And how would you build that? The weight of the blades themselves is going to be tremendous with the current technology. So can we go to lower weight, stronger composite types of materials? There's a lot of research going on in that space. How about embedded sensors? If these turbines aren't turning, they're not generating power, they're not making money, right? And you've probably driven, anybody who's driven through Texas probably seen turbines that aren't running. Typically, if you want to get your turbine repaired, you have to get in the queue because there's only a certain number of rigs that are available. So, to call your wind turbine fix-it doctor, you got to get on the list. So you don't want these things to break down. So can you embed sensors to get a better understanding of current state of health? Maybe you can do some maintenance on it before you get to a complete failure. And the point around wind, when I used to have this debate with the wind program the department manager when I was at Sandia about we're cheating on the price of wind because we're not expecting the same thing out of our variable generators as we are out of our dispatchable generators like a coal plant or like a gas plant. Those, we have full control of the energy source, right? We essentially what we're doing, most of those plants, you're essentially just burning some fuel where Mother Nature has essentially included the storage in the fuel. That's where energy storage happens in those kinds of systems. And then, so you burn the fuel, you heat some water, you turn a turbine, drives a generator, then you get electricity. Wind is not considered dispatchable. Solar is not considered dispatchable. You only get it when the wind is blowing, when the sun is shining. So that's why we have to come up with an artificial energy storage, whether it's batteries, pumped hydro, or some other energy storage, option. So that's a big difference there, and that's why there's so much research going on in. So we've got this grid that's used to operating with dispatchable generation. What's the big deal? Well, now we've got this generation we don't have a lot of control over, not as much control. And people forget the fact that the grid is an electromechanical system, right? We've got inertia when you've got essentially these big magnets that are rotating at fossil-based generation plant or coal or a nuke plant, and they essentially provide that mechanical inertia to maintain frequency. And so now with these other devices, we may artificially have to, with solar, for example, we're using power electronics to compensate and provide that inertia. So lots of opportunity in that space. You know, this seems like a great growth curve as a nation. You know, we're getting closer to 14% penetration, but still about half of that is hydro, right? The majority of our renewables on the grid is still basically dams. And most of that is located in the Northwest. So we haven't made as big an impact nationally as I think we'd like to. Opportunities, though, vary depending where you are geographically in the country. In you know, in the Midwest, lots of wind. In the Southwest, lots of solar. Where's the growth? Where's the load growth, though? It's on the coasts. So the challenge is getting the renewables. You may have the resource, but can you get the resource to where it needs to be used? We have to build transmission lines if we're going to get some large plants. So the option then is to build more distributed types of generation. The big, right, I think the big opportunity where all the action is on the grid is on the distribution side, and we'll talk a little bit about that. So it's not just it's not just the fact that we've got these other options there that are driving some of the change, but also on the load side, and the fact that the consumer is much more educated than they had been in the past. Again, when I was a kid, or even my parents, you know, they just look at the electrical system, or there are a bunch of wires, and magically electricity pops out of the socket, right? That's just what we were used to. But now people are much more engaged. People are understanding that, hey, if I use, if I manage my HVAC system a little bit better, I can actually reduce my energy use. My HVAC system at my house there in Albuquerque, I allowed the utility to come in and disconnect during peak hours. They said, you know, Juan, we'll give you a price break, or we'll give you some sort of a discount, or some sort of a paycheck back, some sort of a check, if you allow us to cut your load at your house during peak times in the summer, because that's when they were struggling to make sure that they met demand. So it's now we're going to a point where the consumer is much more active. So where did we start? If you go back to the Edison days and where the grid kind of started, the general concept is you have a big generator, you have a wire, you get it to a load. One-way power flow, essentially. It goes one direction. Now you can say that we've added different types of generation, mostly dispatchable fossil is what we show here on the left, but of course you can also add the fact that, you know, essentially early on, large wind plants, even large solar plants, same concept. The grid was designed essentially to handle power in this way. It wasn't designed to go the other way. In fact, solar panels, the codes, the standards that are being modified now were set up such that if the solar panels on the distribution system, if the inverter needed to, they work kind of in a master-slave kind of configuration. So they're detecting, the inverter detects, is there power out there? Is there another master device which is going to be the rest of the bulk grid? Is there power out there? If it's there, I'm going to stay on and I'm going to synchronize to it. If it goes away, I disconnect and I shut down. And the reason was for safety purposes. So if there was an issue, they would essentially, if the linemen had to be deployed to work on some disruption that was, say, on the distribution system, they didn't want to have live power feeding back on them. Okay, so that's a huge challenge. So we're changing that with some of the new concepts, where now we've got bidirectional power flow. We can have power coming from the consumer, or what we're calling now a prosumer. So it's a proactive consumer. They can make decisions about power. In some cases, you're looking at things like real-time pricing, where I can choose to turn on say my dishwasher or pool pump or whatever it is at those times when we're not at peak demand, when electricity prices are a little bit cheaper. So you're shifting, the time of the load. And there are a lot of other things that are going on the distribution side with regards to smart meters and smart infrastructure at home. And the big thing is, Internet of Things. Anything and everything is being connected to your home energy management system, to your home internet or your Wi-Fi, and now you're making the system much more complex and increasing what we call, from a cyber perspective, your attack surface. So that has changed significantly. So a little bit more about the work specifically that NREL is doing in this space. So I manage the Energy Systems Integration Directorate, and a centerpiece at NREL and within my directorate is this facility called the Energy Systems Integration Facility, or ESIF. That's what we call it. You always have to have a cool acronym so people remember what it is. It's state of the art. It's been around actually close to 5 years now. We have about 182,000 square feet of space. We've got megawatt scale equipment, inverters, microgrids. We can do hardware in the loop simulation, emulation as well. In the fourth bullet down, petascale high performance computing. I think it's 2.4 petaflops, so that's what, 1,000 million floating point instructions per second. We're going toward a system that's going to be about 5 times this capability. We're in the middle of upgrading this. It's also the most energy efficient system in the world, energy efficient high performance computer. We've got a system there where we run water through these little tubes, and had somebody ask me, what kind of water do you run through that? Because we have a board sitting right out in front of it so you can see the copper tubes. And I said, well, we're in the Denver area. Of course, it's artesian Rocky Mountain spring water, just like what flows through the Coors plant. I got as close to saying beer that as I could. It's not beer. So this is a very, very unique capability. It's also a LEED Platinum building, which you typically don't see, especially at national labs. So we're walking the talk at NREL. Some of the things that we work on, renewable electricity to grid integration. Another area is around vehicles and vehicle to grid, and how we can use those to charge, but also can we use those in situations where we might want to tap into that battery power for backup at a home or at a critical building. So that's some interesting work we've done. Renewable fuels to grid integration, batteries. I mentioned microgrids. That's a huge area of research on how do you advance the concepts around that. And getting to a point where you have intelligence within a system so it knows when to disconnect. A microgrid essentially is, it's a grid that has its own generation, its own way to transport that generation energy, its own loads, and can operate standalone, or it can operate connected to a larger grid. And imagine that the grid is moving in a direction where it was very centralized, big power plants, large transmission lines, and that's how you get your energy, to now the energy is there, but it's also near the load. And we're starting to see it could be a potential patchwork then of a bunch of these things working together. In fact, discussions, I think at the event we went to, right? You start hearing some of these companies where their strategy is essentially going to microgrid-based campuses. That's the strategy. And we're talking about, big companies like Walmart and Google and Amazon and so on. The military as well has kind of said, this is our strategy. We want to increase resilience. We want to have more control over how we use energy, and that it's there for our critical loads. So a lot of work going on in this space. We talked about simulation, cybersecurity and resilience. So this is cross-cutting. It's another major area. Typically, security is an afterthought, especially in the renewables space. Usually don't hear security and renewables in the same sentence. There was this summer, I mentioned, I think at lunch, there was a presentation at the Black Hat Cybersecurity Conference in Vegas this year, where somebody presented, and it was a student from another university, a PhD student, on how they could essentially hack a wind turbine. Okay, so we're moving to the point where, especially as we have more and more of these technologies, have we really addressed security adequately? And have we done it at the very, very ground level as we get to more smart systems, whether it's a smart energy system or a smart transportation, smart bridges, you name it, that we have to have thought about, if it's using digital technology, have we thought about security and where we can embed it early on? Smart homes, energy, water, energy systems. Still, overall, the water usage in the U.S., about 40% of it goes toward agriculture. 40%, about 20% goes toward actual consumption, manufacturing, different things like that, and what we use and what we feed animals and so on. The other 40% is for thermoelectric cooling. Now that doesn't get consumed, it gets put back in the system. But what that tells us is if you've got a coal plant or a gas plant or so on, I have to have water nearby. If I have a nuke plant, I have to have water. So that's really important as well, because water is scarce, especially in the Southwest. Talked already about the high-performance computer, really important in some of our work. So a couple of examples. This is a project we did with Duke Energy. And here what we were looking at is, concern was around increased penetration of solar. But when you have variability, you have clouds coming in, clouds going out, the output of the PV plant goes up and down. And depending on what's going on, it could be trying to send power back out. Well, again, the grid's electromechanical, and you have things like tap changers on transformers that are actually switching back and forth. And you'll wear those out. You'll wear those out because they're mechanical systems. So we're trying to figure out, could we make adjustments on the inverter controls, some of these advanced inverters, so that we can regulate the voltage a little bit better, and we didn't have these extreme switching. So another example, not related to Duke, but on the same topic, one of the challenges we've seen with renewables, a lot of times, you'll have utilities try to couple the fact that they've got a large wind farm and try to compensate for ramping with, say, a gas turbine someplace nearby, because they can ramp up very quickly. And you can usually, they watch the weather, and they've got net towers and different things collecting information, so they can see when the weather, when the wind patterns will change. And if they see things ramping down quickly, they can start kicking in the gas turbines. Well, gas turbines are mechanical systems, right? So there's wear and tear on these systems. So the more and more that they bring them up and down, then the more wear on it. Most of those systems were designed to ramp up quickly and stay on for longer periods of time, not just ramp up and down. So in many cases, utilities have tried to bring in essentially fossil to back up some of their renewables. Let's see, this project, Eastern Renewable Generation Integration Study, is something we did this past year to try to get a handle on what is it, what are some of the challenges that we're up against as we increase renewables on the Eastern interconnect. So if you look at the North American power grid, I think something to remember is our power grid here in the U.S., it's not a U.S. power grid. It's a North American power grid, with the exception of ERCOT. Texas is its own other country, right?
You say the same thing.
Yeah. Right, that's part of the strategy to secede. And so, so you've got the Texas, the ERCOT grid, and then you essentially go up north, and then out to the east, that's the eastern interconnect, and then you've got the western grid, going off in that direction. But they extend all the way up through Canada. So we are intimately integrated with Canada, all our grid, right? Except Texas. So I've got a short video here that we're gonna see how this works. That talks more about this specific project.
We started the study with a question. Can you take one of the largest power systems in the world, one that was designed to work with fossil fuels, and make it work with variable renewables, like wind and solar? We tried to explore what's technically feasible and to identify potential barriers to realizing a cleaner energy future. It's a project that required big models and big data, and it could only be done at the Department of Energy's National Renewable Energy Laboratory. The Eastern Interconnection covers 2/3 of the United States, and it delivers power reliably all the way from New Mexico to Maine. It's a really big system, and one of the most complex in the world. We wanted to know how a system this vast might operate with more wind, more solar, and more natural gas. The questions we looked at in this study have been around for a really long time. We wanted to roll back a lot of the simplifying assumptions that we've been making in the industry for the last 25 years. In the Insight Center, we could see things that we couldn't see in the raw data alone. We were able to animate the time series data, and when we did, a new story began to unfold. Take a look what's happening here. It's late November, and nearly 50% of the generation is from wind and solar PV. Load is low, and we see high amounts of curtailment in the Great Plains until a forecast error unfolds. Over the next 6 hours, the system experiences a 35 gigawatt forecast error, and solar generation peaks at 100 gigawatts. To manage this change in wind, the setting sun, and a rapidly growing evening load, the system needed dispatchable wind and solar resources, quick start gas generators, and the ability to transfer electricity across large parts of North America. This is a challenging set of conditions, but what we saw is that the system still worked. Bottom line, we showed that the Eastern Interconnection can operate at a 5-minute level with 30% wind and solar. Situations like this signal a potential opportunity for new technologies like demand response, energy storage, and electric vehicles. We're looking forward to studying those tools and others as part of the Department of Energy's Grid Modernization Initiative. My work excites me because we're redefining what's possible with clean energy around the world.
Close that guy. I don't think we want to hear him. He might be more interesting, right? All right. So that was some background. And I don't know if you noticed, you could see essentially the sun setting, sun coming in, and then the yellow was solar and how it grew during the day, and then the blue was wind and how that increased at night. That tends to be how things work. You get more wind at night. So another project we did, how many of you saw the Eclipse this summer? Yeah? I missed it. I was on a plane. I didn't get a chance to see it. But the trajectory there, if you look at the right panel, that essentially shows the path that was most affected by the eclipse. The video on here isn't quite working, but essentially what we were looking at is the left was kind of what we anticipated if there was no eclipse. And we were able to do some simulation in advance to get an estimate of how much impact we'd see on the grid from solar generation. Okay, so this is really, really important kind of work to help us to understand whenever we do have some predictable kind of major disruptions on the grid. We can do some as well with things like the big storms. Right now with Puerto Rico, we're working on how we can make their system more resilient, providing some planning. Does it make sense at any point to add renewables, or at a minimum, we're looking at microgrid kind of technology to harden the grid. So if you lose a transmission line, you could potentially have underground cables at the distribution level, and some local generation at distribution for critical loads like hospitals, like maybe military government facilities and so on, or at areas tend to be like emergency congregation centers, where we try to get people to collect in advance of a storm. We did this kind of work as well in response to Katrina, to help for future types of impacts in the Gulf, have energy where you really need it. So these are new concepts that haven't, you'd think right now we should have thought about this before, but the technology really wasn't there. Microgrid concepts, that just wasn't how utilities operated. In fact, I'd say about 10 years ago, I had a conversation with the utility, actually from Texas, from a city south of here, we'll just say that. And they, I remember bringing it up to that person, hey, what do you think about microgrids and how we can start to incorporate them in how you operate for critical loads? And said, you know what, microgrids are boutique novelty. They'll never fly. You'll see a couple of them here and there. Now it's becoming more of the norm as to how we're preparing for those kinds of systems, for those kinds of events. And here's an example of where we're applying that. This is some work with Wiley and the U.S. Army. Wiley being one of the big vendors, and what they want. Well, first it's important to know why is the military thinking about these concepts? Well, if you look at how many lives were lost during, say, our time in Iraq, it was about 1 in 11 were lost in logistics, transporting water and fuel. So it's a lot of people died just moving fuel. So these are the big convoys and so on. So they want to reduce their energy footprint as a whole. This particular system, a consolidated utility-based energy cube, is a microgrid, essentially central control system. And you can connect here different types of generators, and then you can set it for optimizing based on, depending on what you have on there. Do you have some solar? Do you have some diesel gensets, and so on? And so you can set it to dispatch depending on what the need is. First use this kind of generation, but if the load grows, then kick this one in, and so on. And this is set up to be in a form factor to be transportable. So you can put it on a C-130 and take it wherever you need to, transport it by truck, and so on. So this is pretty interesting work as well. On the electric vehicle side, there's quite a bit of work going on in that space with pretty much anybody who's developing vehicles right now is considering where they're going in the electric vehicle space. GM is one of our partners. We work with Nissan, with Toyota, you name it, Honda. And in this case, we're looking at improving the performance, durability of some of these fuel cell technologies and making them more manufacturable and easier to maintain long term. So this is one of my favorite projects, Hawaii. I spent about 4 years going to Hawaii, back and forth about once a month. And I complained to my boss about it one time, and he laughed. He did exactly that. He said, "God, this travel's just wearing on me." I said, "Come on, you're going to Hawaii. There are many worse places to go." So this is under the Hawaii Clean Energy Initiative. But more recently, this particular project is Hawaii's trying to get to the high penetration of renewables, 100% of their energy through energy efficiency and clean energy. They're putting in a lot of solar. The policies, this is where, again, the policy and the technologies and everything has to align. Policies were put in more solar. The utility got to a point where they said, wait, our grid is not that rigid. We're not able to borrow power from a high inertia system next door, like say in the US, where we've got big inertia systems, coal plants, nuke plants, and so on. They literally, their grid is an island. And so it's very soft. Their power plants are smaller typically than what we find here on the mainland. And so small perturbations in load, smaller than what would actually cause a grid here to go unstable, affect their frequency. And so they told everybody to hold off. Well, people were not happy when they're told, I just invested a bunch of money to put solar panels on my house, and you're telling me I can't even use it? I can't connect it I can't connect it to my meter or anything like that. So HECO, the Hawaii utility, came to NREL and said, can you help us out here? Now, we did some modeling, we did some analysis, and said, you know, with these smart inverters that the current state of the art, we could propose some algorithms for control so that they respond better and provide some of that support, voltage support, frequency support that you were not expecting and you probably couldn't get on some of the older inverters. So now they're up and going, a lot more solar going in, and so that's a really big success story. So one of the big initiatives going on here in the U.S. under Department of Energy is grid modernization, getting toward resilient, reliable, secure, sustainable, affordable, flexible. All the ILITs is usually what we call them. And how do we get there? You know, when is grid? People ask me, when is grid modernization over? When is the grid modern? Isn't it modern now? Hasn't it been modern? The real answer is you're never really quite done, but it's getting on a trajectory for where the grid should evolve. So that right now, you know, we're still essentially trying to update and upgrade a 57 Chevy. And we're putting in new bells and whistles, we're adding GPS and all these different things. So the idea is to get this going in a direction so in the future, as new technologies come in, it becomes a better framework for supporting these different aspects of grid modernization. And it's supported through Grid Modernization Lab Consortium. So if you look at the top, the two co-lead labs are Pacific Northwest and NREL. I'm the NREL person there, we co-lead this. 13 labs. There are 6 teams as well involved around institutional support are some of the soft things, business models, regulation, devices, integrated systems, sensing and measurement. So there are research initiatives going on in each of these. So there's a $200 million investment in this space that all the labs right now are working in. I lead, if you go to the bottom, I also lead the security resilience team. So there's quite a bit in that space. And we're moving towards something we call all hazards resilience, which is not just resilience to storms, but resilience to cyber threats, resilience to physical threats, which still happen. We talked a little bit at lunch about that one, even a recent physical attack on the grid. I think it was 2014, Boston City Marathon. When all that was happening, people were focused on that. There was actually an attack on the PG&E, Pacific Gas and Electric Grid in the Bay Area. Physical attack on their cyber system, cut communication lines, and then shot transformers. So those kinds of things still happen. We're going to jump over to cyber for a second because that is just right now it's just a huge area. What do we do? What do we do about it? I've had people tell me, should I just give up because we just assume everything is just vulnerable. There's a lot of interest in this space. If you look at the slice of the pie down at the bottom around energy, these are the different sectors with regards to interests by adversaries. A lot of these are actually attacks that cause some sort of a major impact. So manufacturing was the biggest. These are infrastructures. No, this isn't banking necessarily. These are systems. A lot of these systems had actually physical consequences associated with them. That's the big difference. So what should we do about it? What's the cost? Who's responsible for security? We all want cheap electricity, right? We all want to pay our 8 cents a kilowatt hour. Yet this infrastructure is the target of terrorists, cybercrime, foreign nation states. So, and had the conversation earlier today. Joke has been, and don't quote me on this, but I believe there are some references behind it. Is that the utility sector spends less in research than the dog food industry, right? So if you want to go into research, go into dog food. The point being there that they have a lot of restrictions, right? They can't just raise the rates for electricity. So who's responsible for it now when we're trying to protect it against these different adversaries? And then, that's not even touching foreign nation states. I don't know if anybody saw a couple of weeks ago, there was a lot of chatter around the fact that North Korea had had spearfishing exercises that were being sent to utilities, trying to get utilities to bite. If you look at what happened in 2015 with the Ukraine power grid attack, that started with spearfishing. And so it's some of it is awareness. If you look at Equifax, I don't know where all my personal information is or where yours is, but that was a major catastrophe. It's not just technology. So how did security fail there? And really, a lot of it is awareness and understanding. You don't just click on stuff when they send it to you. Pay more attention to it. So there's this cultural aspect. Another driver potentially, if you look at this report on the right from Lloyd's of London, was looking at insurance as a driver. How can you incentivize more investment in security through insurance requirements? I mean, if I buy a house that's in a flood zone, I'm going to pay more. I'm going to buy flood insurance. I'm going to pay more for it. So is this a way to actually maybe increase the vigilance in that particular space? A major challenge around the grid and the infrastructure, and so especially around renewables, there are not a lot of right now. Security typically isn't used in the same vocabulary with discussion around renewables. And as we get the penetration much higher, then if we haven't thought about it early, then that's a huge challenge. And bolt-on security just doesn't work. It doesn't work well, and it's also it's much more expensive. So those of you that are doing research in this in infrastructure or interested in working in this particular space, I think it's important to note that we are moving towards more smart infrastructures, smart transportation, autonomous systems, smart, you name it, smart vehicles, and so on. Usually, smart implies digital technology somewhere in there. So I would ask you to become more aware of what some of those security concepts are. What can you do as we move forward with designing next generation of systems? We still have to somehow figure out how to secure the old systems, but in the future, how do we get toward more inherently secure and I would call resilient systems? We're always behind when it comes to security. We never know what the next threat is, what the next vulnerability is that we're going to find. So how can we get to systems that are more inherently resilient? Given that something will happen, can it isolate that part of the system? And how can it recover and heal itself much more quickly? So how do we build that in? So I think there's a huge opportunity there for us to change things. The big intent here is, how do we get on a better path and design an infrastructure that we think we really want, as opposed to a system that's been essentially built out with, I guess, more of an opportunistic approach. This is there, this is cheap, let's put it in. Let's connect to it because here's an opportunity to make some extra money or reduce our costs. That tends to be the way we operate. So how can we be more intentional and more strategic about this? All right, so I'll close out with that and open up to questions. All right, thanks.
Do you have any work on EMP?
I would say yes, the labs do. And I'm involved right now with the Colorado EMP Task Force. That definitely continues to be a threat. For those of you that don't, EMP, electromagnetic pulses, which could be from weapons like nuclear weapons, or it could be directed energy types of weapons as well.
So
and GMD, geomagnetic disturbances.
Is there a reasonable solution that you're working towards?
Is there a solution? First of all, yeah. Where the challenge comes in typically with EMP is that an event like that induces a current on long transmission lines. So if you can minimize the number of long transmission lines or find ways to isolate that, yes. The challenge is the cost. It's not cheap. You know, people have said, can we go to DC lines? It's very expensive. So there are people that have proposed solutions, and it's always a balance of risk and cost. You know, is the risk high enough that I'm willing to invest this amount of money toward changing and resolving it, or can I live with it and maybe not totally eliminate it, but reduce the potential consequence at certain key areas? So yes, the labs are working on it. I don't know that there's a reasonable solution yet.
Just follow up on that. I remember back in the days, the former USSR, they had those super long transmission lines through their Siberia, and they encountered this type of problem. Do you know what kind of solutions they actually found to solve that?
Yeah, yeah. So the question was, in the Soviet Union, right? They had that issue in Siberia with some of these long transmission lines, and the question was, you know, how did they solve that solution? I don't know exactly what they did. You know, and the thing, I think there's a big difference there as well. In the Soviet Union, I believe that the government has much more control of their infrastructure. I was asked this question on Tuesday at the conference when I gave this presentation is, so should we, given the threat and where the threat has changed, should we move toward a government-owned infrastructure, government-owned electricity infrastructure and so on? I said, you know, good luck with that one. I just don't think it's reasonable. There's just way too much momentum. You would wipe out an entire industry essentially, or you'd significantly have to change that. The cost of doing that is just tremendous, and I don't know if that's reasonable. There are some countries actually that do have government-owned or government-controlled infrastructure for security reasons and so on. So they may have implemented some of the solutions that we've considered, but because the government owned it, they sucked up the cost somehow, taxed the heck out of people to get there. And you always get the pushback, right? If this is an additional tax, you know, on the average citizen, people say, well, wait a minute, is the risk high enough? Is it worth you taxing me that much? So they may have implemented some of these solutions. Yes?
I've been reading reports that one of the barriers to adoption of energy storage on the East Coast is that lithium-ion batteries, such as Tesla has, could burn at a very high temperature, and the firefighters don't know what to do about this yet, especially in New York City. Do you have anything to say about lithium-ion battery safety, and are you aware of lithium ferrous phosphate batteries that are not flammable? The technology was developed here at UT Austin.
Okay. So I have an opinion. I don't know that I can necessarily talk about the lithium ion phosphate, but here's where we're going is storage right now we're looking at as kind of it's a silver bullet. Lithium ion, you know, we're still trying to figure out, can we get the cycle life? Can we get the size and so on? Can we get the cost down? Can we address the safety issues? Ideally, I think, you know, discussions we've had about about storage in general has been, you know, we'd like to get to the point where even at home, if you have a PV system, you can go to Home Depot and buy your battery and stick it, you know, put it in your garage or whatever and plug it into your system and you're done. We're not anywhere near there. I think we're still trying to figure out the storage piece. I'll add one more thing as well. There's a safety aspect. I think we still don't know. We don't have a full solution. I think there's still a lot of data being collected on that. But you know, the other piece of this that we usually don't think about this early enough on is the supply chain, and the fact that some of these technical solutions require rare earth materials as well. And we could position ourselves as a nation to a very similar model that we were in a paradigm such that we were reliant on the Middle East for oil for many years, that we may be reliant on some certain material from certain countries, because now we're reliant on this battery storage technology. So there is some concern there, is great technical solution, but does it really make sense for us as a nation? Would at some point we'd have to wean ourselves off of lithium ion, because now we're dependent on it from a supply that isn't stable.
I was just wondering if you'd comment a little bit about market design. Earlier in your talk, you'd mentioned that our expectations from fossil fuel systems versus the renewables is distinct, but I would argue that in the ERCOT market, they're bidding in the same as anybody else, and they're penalized for not delivering, just as a fossil fuel plant would be penalized if they had a mechanical failure and failed to deliver. So are there just can't we rely on our market designs, or do you have any comments about how we should design our markets to encourage the investments we need?
Yeah, so I don't know that I necessarily have a solution. I think there's still opportunities to improve the markets. There are additional aspects as well to the cost that are included in, that utilities are struggling with, which is especially in places as essentially they've been thinking about distribution level generation as negative loads. So that what that does, then it potentially, in some cases, could affect the cost, because that now affects the amount of load that they're trying to serve. I would also say that utilities are struggling with how they recoup the cost for managing the infrastructure for distribution systems, especially. And even in New Mexico, what we started to see there is they went to some new system where they were they were asking people if they wanted to pay extra to get green electrons. Okay. I think we're moving in a better direction. I don't think there's a perfect market yet. And as the level of penetration increases, I don't know that the current models necessarily will work the same way. So there are a lot of folks working on different studies around that area. I'm not an expert on that topic, but the discussions that I've had are there's still some opportunities where they need to change. Question over there?
Yeah, just one other barrier, I suppose, that I had read about to widespread adoption of some of the technologies you talk about, like smart inverters, like they had in Hawaii, and just interconnection of DER on the grid, is that there seems to be a lot of the technology is getting to places where you can theoretically do these things, but there isn't the standards or the engineering standards that actually support widespread implementation of these things. Does NREL have a role in developing these standards so that they can be applied in utilities everywhere, and why does that sort of stakeholder process take quite a long time, it seems?
Yeah, so let's see, we have anybody ever been involved in standards development? Okay, since you haven't, then you probably don't, it is painful. Yeah. It's a long process, and maybe quickly just explain how the standards process works. So yes, NREL is involved. We're not standards makers. We typically inform, or maybe are in the process to help validate whether or not the standard makes sense. So we're able to test how they might be implemented. The way the standards typically work is there's a need identified by an element of the, say, a sector. Let's just say inverter interconnection or something. Then through a standard body, it could be IEC, International Electrotechnical Commission, then the interested parties get together, and you usually have vendors involved. You may have some of the potential implementers and users involved as well. And the reason they take so long is because they're essentially are a consensus kind of process. And you'll have vendors that will jockey for position, that will say, well, wait a minute, if the standard goes this way, it'll really benefit me. So they will try to drive it that way. And another vendor will say, well, wait a minute, if it goes that direction, this will benefit me. So there's, there's a lot of personal business interest in that, and it takes a while. So the labs do participate on these and try to provide some neutral, objective input. So in the end, we get something that is good for the majority, right? Some people are, you're not going to please everybody. You're not going to get everything out of it, but that's why the process takes a while, and it's got to get reviewed, and then it's got to do some sort of a validation and so on. So, but it's a good question because standards are really a real important part of this. Any more questions?
Well, thank you very much, Juan. We really appreciate the presentation.
Thank you.